Tonight, we're going to ask a question that sounds like it already has an answer. Can we actually survive Mars? For 60 years, the answer we've been given, by scientists, by billionaires, by entire space agencies, has been some version of yes, confidently, on a schedule. Early 2020s. By 2024, the 2026 launch window. Every few years, a new date arrives, stated with total certainty, and every few years, that date quietly passes unmet. But here's what most people don't realize. Buried underneath all of that confidence is a single number that nobody on Earth can fill in. Not an estimate, not a range with error bars. A genuine, total blank. We have sent astronauts to zero gravity for over 3 decades. We understand, in exhaustive detail, what happens to a human body floating in orbit. We have equally exhaustive data on what a human body does at Earth's full gravity. That's every hospital, every gym, every textbook of medicine ever written. But Mars sits at exactly 38% of Earth's gravity. Not 0, not 1. Something in between. And in the entire history of human spaceflight, no person, no mouse, no plant has ever been tested at that specific gravity for any meaningful length of time. Not once. We are planning to send human beings to live and work on a world whose single most basic physical condition, the pull of the ground beneath their feet, has never been tested on a living human body at all. And that gap is only the beginning. The first surprise is what the Martian atmosphere would actually do to an unprotected human body. And it isn't what Hollywood has told you. The second surprise is a radiation number so large that a single round trip already breaks NASA's own safety limit before the crew has spent a single day on the surface. The third surprise is that the psychological danger of a Mars mission isn't really about loneliness at all. It's structural, built into the geometry of the solar system itself, and there is no evacuation, ever, from the moment the spacecraft leaves Earth orbit. And the fourth surprise is the most quietly devastating one. We may have already found the single strongest hint of ancient life ever discovered on another world, sealed in a titanium tube sitting on the Martian surface right now, with no funded mission to go and bring it home. By the end of tonight, you're going to understand exactly what it would take for a human being to survive on Mars. The atmosphere, the cold, the radiation, the isolation, the food, the landing, the going home again. And why, after 60 years of confident predictions, the honest answer is still genuinely, fascinatingly uncertain. Before we dive in, if you're someone who finds this kind of deep, honest exploration of the universe genuinely calming, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Long before anyone asked whether we could survive on Mars, Mars had already spent thousands of years quietly breaking human attempts to understand the sky at all. To the naked eye, watching night after night, almost everything in the heavens behaves with perfect, predictable discipline. The stars wheel around in fixed patterns. The sun rises and sets on a stately annual rhythm, but a handful of points of light. The ancients called them wanderers, which is where the word planet comes from, refused to follow the same simple rules. And of all of them, Mars was the worst behaved. Watch it carefully over several months, and it does something genuinely strange. It slows down against the background stars, stops entirely, reverses direction and drifts backward for weeks, stops again, and then resumes its normal forward path. Retrograde motion. It was the single hardest observation for the old Earth-centered model of the universe to explain, forcing astronomers into increasingly elaborate, increasingly desperate systems of circles within circles just to make the mathematics match what any patient observer could see with their own eyes. The resolution didn't come from a better theory. It came from a man willing to trust a number smaller than anyone thought mattered. The Danish astronomer Tycho Brahe spent roughly 20 years recording planetary positions with nothing but the naked eye, achieving a precision of 1 to 2 arc minutes. very close to the physical limit of what a human eye can resolve without a telescope, which hadn't been invented yet. When Johannes Kepler inherited that enormous data set after Tycho's death, he tried again and again to fit Mars's orbit to a perfect circle. The shape every astronomer since antiquity had assumed the heavens must obey, because circles were considered the only shape worthy of the perfect celestial realm. It almost worked. The residual error between the circular model and Tycho's actual measurements was only about 8 arc-minutes. For context, that's roughly the width of a single human hair, held out at arm's length against the vastness of the sky. A discrepancy so small that almost any other astronomer in history would have shrugged, called it observational noise, and rounded it away. Kepler didn't. He trusted Tycho's data more than he trusted 20 centuries of philosophical assumption about the perfection of circles. And that refusal to discard an error smaller than a hair's width produced the elliptical orbit and the first 2 laws of planetary motion, published in 1609. The mathematical foundation on which every spacecraft trajectory to Mars, including the one that will someday carry a human crew, still depends today. Modern celestial mechanics. The entire discipline that makes a Mars mission possible at all exists because one man refused to round away a hair's width of error. That's where this story actually begins. Not with rockets, with stubbornness. If Kepler's story is about the value of trusting small data, the next chapter of Mars's history is the opposite lesson entirely. A story about how confidently, how elaborately, and for how long human beings can be wrong about a whole world, working from almost nothing at all. In 1877, during an especially favourable alignment of Earth and Mars, the Italian astronomer Giovanni Schiaparelli turned his telescope toward the planet and mapped a network of faint linear features across its surface. He labelled them canali, Italian for channels, a plain, neutral geological term, the kind you'd use to describe any natural drainage feature. Something was lost crossing the English Channel. Rendered into English, canali became canals. And a canal, unlike a channel, is not a thing that occurs in nature. A canal implies a builder, an engineer, a civilization. Percival Lowell, a wealthy Boston businessman with a serious scientific hunger and no shortage of resources, seized on the idea and built an entire observatory in Flagstaff, Arizona specifically to chase it, choosing the high desert altitude deliberately for the steadier air it offered his telescope. Over the following years, he wrote 3 books, each more confident than the last. Mars in 1895, Mars and its Canals in 1906, and Mars as the Abode of Life in 1908. His vision was elaborate, coherent, and this is the part worth sitting with, genuinely seductive. A dying, desiccating world, its oceans long gone, whose inhabitants had engineered a planet-spanning irrigation system to drag meltwater from the polar caps across thousands of miles of desert to their equatorial cities. He mapped hundreds of individual canals in painstaking detail and gave each one a name drawn from classical mythology. It was wrong. Not carelessly wrong. Persuasively, meticulously, confidently wrong. The canals, it turns out, were never on Mars at all. They were inside the human eye. When your visual system strains to resolve a field of scattered, low-contrast dark patches at the very edge of what your instrument can distinguish, your own visual cortex has a well-documented habit of connecting the dots into lines. The exact same mechanism that lets us see constellations in randomly scattered stars or a face in the shadows and craters of a distant hillside. Alfred Russel Wallace, the co-discoverer, alongside Darwin, of natural selection, published a book-length rebuttal in 1907, arguing on pure thermodynamic grounds that Mars was simply too cold and its atmosphere far too thin to support flowing surface water of any kind, let alone an irrigation network. Wallace was completely correct. He was also almost entirely ignored. Lowell's vision was too vivid, too complete, too emotionally satisfying to let go of for a few dry equations from a rival. The empirical correction, when it finally came, was total and merciless. On July 15th, 1965, a small spacecraft called Mariner 4 flew past Mars and radioed back 21 photographs covering roughly 1% of the planet's surface, about 600,000 square miles. No canals, no cities, no vegetation. What the pictures showed instead was a heavily cratered, apparently dead surface, eerily reminiscent of the Moon. News coverage at the time was, by every account, funereal. An entire imagined civilization, elaborately constructed over 70 years of confident scientific writing, evaporated in the space of a single afternoon's data transmission. But here's the detail that almost never makes it into the popular story, and it's the one worth sitting with the longest. Mariner 4 didn't just correct the myth of the canals. It overcorrected and created a brand new myth in its place. Because that spacecraft happened, purely by the accident of its flight path, to photograph 1% of the surface. And by chance, a heavily cratered, ancient, geologically quiet region in the southern hemisphere. Based on that single unlucky sliver, the scientific consensus shifted, almost overnight, to a new confident conclusion. Mars was a dead world, geologically inert, a cratered rock, no different in essence from the Moon, with nothing more to discover. It took 6 more years and a second spacecraft to correct the correction. Mariner 9 arrived in 1971 as the first spacecraft ever to orbit another planet, and rather than sampling one narrow strip, it mapped the entire globe. What it found overturned the dead rock consensus just as completely as Mariner 4 had overturned Lowell's canals. Olympus Mons, the largest volcano in the solar system, nearly 3 times the height of Mount Everest. Valles Marineris, a canyon system so vast it would stretch across the continental United States, and threaded across the ancient highlands, the unmistakable branching pattern of dry river valleys. The fingerprints of a world that once, billions of years ago, actually had liquid water flowing across its surface. The pendulum had swung twice in a single human generation, from an imagined civilization to a dead rock to a world that once had rivers. Each swing was made by careful, serious scientists, using the best data available to them at the time. Each one felt, in its moment, like the final word. This channel keeps returning to stories like this one, again and again, because the lesson never really changes. Confidence is not the same thing as correctness, and the universe has an almost limitless patience for letting us be thoroughly, elaborately wrong before it shows us more. Keep that pattern in mind, because tonight, when we talk about crewed Mars missions arriving in the late 2030s, or Mars becoming humanity's second home within a generation, we are listening to exactly the same kind of confident, well-intentioned, and possibly premature certainty that built Percival Lowell's canals. Before we get into what it would actually take to survive there, it's worth answering a question that rarely gets asked directly. Out of every other world in the solar system, why Mars specifically? The honest answer is unglamorous. Mars is not a good place to live. It is, by a meaningful margin, simply the least bad place available. Consider the alternatives one at a time. Venus, in one specific narrow sense, looks almost inviting. It has nearly Earth's own gravity, about 90% of ours. And if you climb to roughly 50 kilometers above its surface, into the layer of its atmosphere where pressure and temperature happen to closely resemble Earth's own, floating city concepts genuinely make physical sense. But the actual surface of Venus is a 464 degrees Celsius furnace under 9.2 megapascals of pressure, 92 times Earth's own atmospheric pressure, an environment so punishing that it has destroyed every single lander ever sent there within about 2 hours at most. The Soviet Venera 13 probe holds the endurance record, and it lasted 127 minutes before its instruments failed under the heat and crushing pressure. There is no accessible water on Venus, and there is no plausible pathway to live off the land there at all. The Moon offers something genuinely valuable: proximity. It's 3 days away, not 8 months, which makes it the correct place to practice everything before attempting Mars for real. But its day-night cycle lasts 29.5 Earth days, meaning any given spot on its surface endures roughly 354 continuous hours of darkness. Nearly 2 full weeks with no sunlight at all, a brutal problem for both power and temperature control. It has no atmosphere whatsoever, which means no aerobraking to slow an incoming spacecraft, no carbon dioxide to harvest as raw material, and no atmospheric shielding at all against radiation. Everything that reaches the lunar surface reaches it directly and completely. Titan, Saturn's largest moon, is stranger still. It has a thick nitrogen atmosphere at a pressure a human body could actually tolerate without a full pressure suit. Genuinely remarkable among all these worlds. But at nearly 180 degrees below 0 Celsius and receiving barely 1% of the sunlight Earth gets, solar power there isn't just difficult, it's essentially not viable at all. Every material you might build with behaves like something else entirely at that temperature. Mars, by comparison, offers a specific, unglamorous, but genuinely decisive combination of advantages. Its atmosphere is thin enough to land through relatively simply, yet thick enough to aerobrake against, and thick enough to mine directly for carbon dioxide. It holds water ice in industrially useful quantities. Its day is 24 hours and 39 minutes. Within about 3% of a human being's natural circadian rhythm, which matters more than it might sound. It receives enough sunlight that solar power is merely difficult, not physically impossible. And it has a real axial tilt, close to Earth's own, which means it actually experiences seasons the way we understand them. None of this makes Mars comfortable. It makes Mars possible. That's a very different, much lower bar. And it's worth remembering that distinction for everything that follows tonight. There's one more piece of context worth understanding before we get into the environment itself, because it explains why you can never simply decide to leave for Mars on a Tuesday. Earth and Mars orbit the Sun at different speeds, which means the two planets line up favorably for an efficient trip only once every 779.9 days, roughly every 25.6 months, and each such window lasts only a few weeks. Miss it, and you wait more than 2 years for the next one. Here is the detail that surprises almost everyone the first time they hear it. The amount of rocket energy required to leave Earth's orbit and head toward Mars is roughly 3.6 kilometers per second of delta V. The amount required to head toward the Moon instead is about 3.2 kilometers per second. Those two numbers are remarkably close. Getting to Mars, in other words, is not primarily an energy problem at all. It's a time problem. The Moon costs you 3 days of consumables, life support, and radiation exposure. Mars costs you somewhere between 200 and 270 days each way. Plus a surface stay dictated entirely by celestial mechanics, not by anyone's preference. You cannot simply decide to go faster and get there sooner by much. The orbits themselves set the terms. And that single fact, that Mars is not reachable on a schedule of human convenience, turns out to shape almost everything else about what a real mission there would actually require. Now let's actually stand on the surface. Because the first thing that would happen to an unprotected human body on Mars is not what most people, raised on decades of science fiction, assume it would be. Mars has an atmosphere, technically. Average surface pressure comes out to about 610 pascals, roughly 0.6% of Earth's sea level pressure of 101,325 pascals. To find an equivalent on Earth, you'd need to climb to roughly 35 kilometers above sea level. More than twice the cruising altitude of a commercial airliner, well above 99.9% of the mass of our own atmosphere. There's a specific number in human physiology called the Armstrong limit, 6.3 kilopascals, the pressure at which water boils at normal human body temperature, 37 degrees Celsius. Mars's average surface pressure sits at roughly 1/10 of that limit. Sit with what that actually means. On the surface of Mars, without a pressure suit, the saliva on your tongue would begin to boil. The moisture lining your eyes would begin to boil. The thin fluid coating the inside of your lungs would begin to boil. Not because Mars is hot. It categorically isn't, as we'll get to shortly. But because there simply isn't enough surrounding air pressure to keep water in its liquid state at body temperature at all. Here's where we need to correct a myth that has shaped almost everyone's intuition, courtesy of decades of Hollywood movies showing unprotected astronauts violently exploding the instant their suits are breached. That is not what happens. Human skin and the human circulatory system are considerably tougher, structurally, than fiction gives them credit for, more than strong enough to contain the body's own internal pressure against an external vacuum. We actually know exactly what happens because it has already occurred, once, by accident, here on Earth. In 1966, during ground testing at NASA's Johnson Space Center, a technician's pressure suit lost its seal inside a vacuum chamber, exposing him to near-vacuum conditions. He remained conscious for approximately 14 seconds before losing awareness, when he later recovered, because his colleagues were able to repressurize the chamber in time. His own account of those final moments of consciousness was strikingly specific. His last clear memory was the sensation of the saliva on his tongue beginning to boil. He did not explode. He did not freeze solid. What actually threatens a human body exposed to Mars's near-vacuum atmosphere is hypoxia and something called ebulism, the formation of gas bubbles in bodily fluids, playing out over roughly 10 to 15 seconds of useful consciousness and death, if unaddressed, within a couple of minutes. Serious, genuinely lethal, but nothing like the movies. This is shocking discovery number 1 for tonight. The single most viscerally frightening image most people carry about unprotected exposure on Mars, violent, explosive decompression, is simply wrong. The truth is quieter, stranger, and in its own way, more unsettling. Your own body's water, boiling gently away at a temperature that feels perfectly comfortable. Pressure is only the first problem. What that thin Martian air is actually made of is the second, and in some ways more consequential. Mars's atmosphere is 95.1% carbon dioxide. Everything else humans actually need, nitrogen, oxygen, exists only as vanishing traces within an already vanishingly thin total. Nitrogen makes up 2.59% of that already thin 610 pascals, which works out to a partial pressure of roughly 16 pascals. Earth's own nitrogen partial pressure, by comparison, sits at approximately 79,000 pascals. That's a difference of roughly 5,000 times. This matters enormously, and not just for breathing. Nitrogen is the essential building block of proteins, the foundation of agriculture as we understand it on Earth. A Martian atmosphere with 1/5000th of Earth's available nitrogen represents, according to the research, the single genuine bottleneck standing between Mars and any future large-scale farming. Extracting usable nitrogen for fertilizer means processing staggering volumes of already thin air, just to gather a meaningful quantity of one specific trace gas. Oxygen fares even worse. At 0.161% of an already thin 610 pascals, Mars offers a partial pressure of roughly 1 pascal. Earth offers about 21,200 pascals. That's a difference of roughly 21,000 times. Here's a way to actually feel these numbers rather than just hear them. If you took the entire column of Martian atmosphere sitting above 1 square meter of ground and compressed it down to Earth's own sea level density, you would end up with a layer of air roughly 17 centimeters thick, about the height of a paperback book standing on its end. Do the same thing with Earth's atmosphere, and you'd get a column roughly 8 kilometers tall, 17 centimeters against 8 kilometers. That's the entire available cushion of air on Mars, compressed down to something you could hold between 2 hands. And even within this well-understood, thoroughly measured picture, Mars still has one active, completely unresolved mystery hiding inside it. Over 3 full Mars years of continuous monitoring, the Curiosity rover's onboard chemistry laboratory found that atmospheric oxygen levels rise during spring and summer by as much as 30% above what all known atmospheric chemistry predicts they should, and then drop back down again in autumn on a repeating seasonal cycle. Argon and nitrogen, monitored by the same instrument at the same time, behave exactly as expected, rising and falling in perfect agreement with the models. Oxygen alone refuses to cooperate. No confirmed mechanism exists to explain it. It is almost certainly some geochemical process we simply haven't identified yet, rather than anything more dramatic. But as of right now, nobody actually knows what is producing it. It remains genuinely an open question. Now let's talk about temperature, because Mars's cold turns out to behave in a way that has no real equivalent anywhere on Earth. The global average surface temperature on Mars is about 210 Kelvin, minus 63 degrees Celsius. For calibration, the single coldest air temperature ever directly measured anywhere on Earth's surface was minus 89.2 degrees Celsius, recorded at Russia's Vostok station in Antarctica on July 21st, 1983. So an average day on Mars is remarkably warmer than the coldest moment Earth has ever produced. But Martian winter poles plunge to roughly minus 153 degrees Celsius, 64 degrees colder than anything Earth's surface has ever recorded, cold enough that carbon dioxide itself freezes directly out of the thin atmosphere as dry ice frost, coating the ground. There are two specific features of Martian cold that make it behave unlike anything in ordinary human experience. The first is the sheer size of the daily swing. Because the atmosphere is far too thin to hold on to heat the way Earth's thicker air does, surface temperature on Mars can vary by 80 to 100 Kelvin across a single day. An equatorial afternoon in summer might reach a genuinely pleasant plus 20 degrees Celsius at ground level, and then plunge below minus 70 degrees before the following dawn. The same patch of ground, the same day, swinging by nearly 100 degrees. The second feature is stranger, and it's the one that should genuinely unsettle you. With so little atmospheric mixing to even things out, the temperature difference between the ground itself and a point just 1.5 meters to 2 meters above it, roughly head height for someone standing, can be tens of Kelvin apart during the daytime. Instruments on the Viking landers, on Curiosity, and on Perseverance have all measured this directly. Standing on the Martian surface in daylight, your boots and your head would, quite literally, be sitting in two measurably different climates simultaneously, a temperature gradient far steeper than anything that exists anywhere in Earth's lower atmosphere. And at night, that gradient flips entirely. The ground itself becomes colder than the air sitting just above it. The practical consequence is worth stating plainly, because it upends the obvious intuition. Designing a Mars suit or a Mars habitat is not simply a matter of insulate against the cold. Both temperature extremes exist within the same single vertical meter of space, and they physically invert themselves in place twice every single day. Here is the discovery that, more than any other single fact in this entire story, quietly determines whether a real human Mars mission is even survivable within the safety standards we currently hold ourselves to. Mars lost its global magnetic field somewhere around 4 billion years ago. Without that protective magnetic shield, the solar wind has been continuously stripping the Martian atmosphere away into space ever since. NASA's MAVEN spacecraft measured the present-day loss rate at somewhere between 1 and 2 kilograms of gas per second, escaping permanently into space. Isotopic measurements of argon, a chemically inert gas that can only leave a planet by directly escaping to space, since it doesn't react with anything, indicate that roughly 65% of all the argon Mars ever had is already gone. A tracer for a far larger, ongoing loss of the planet's original atmosphere and, with it, its original radiation shielding. What remains above your head on the Martian surface amounts to about 16 grams per square centimeter of atmospheric shielding, compared with roughly 1033 grams per square centimeter on Earth. Mars offers, in other words, about 1.5% of the atmospheric radiation protection Earth provides. Some of that loss is offset by the simple fact that the planet's own bulk blocks half the sky beneath your feet. But the numbers that remain are genuinely severe. NASA's Curiosity rover carries the first radiation dosimeter ever operated on the surface of another planet, and its measurements give us real, hard figures rather than theoretical estimates. On the Martian surface, in Gale Crater, the dose rate comes out to 0.64 plus or minus 0.12 millisieverts per day. Annualized, roughly 233 millisieverts per year. Earth's own natural background radiation, from cosmic rays and the ground itself, averages about 2.4 millisieverts per year. Do the division, 233 divided by 2.4 comes out to roughly 97. A single year standing on the surface of Mars delivers, in radiation terms, roughly the equivalent of 97 years of ordinary life on Earth. And the surface isn't even the worst part of the journey. The cruise phase. The roughly 6 to 9 months spent in deep space, simply getting there, is considerably more dangerous because on the Martian surface the planet itself blocks about half of the incoming radiation, whereas in open interplanetary space, cosmic rays arrive from every direction at once, all 4 pi steradians of the sky simultaneously, with nothing at all standing in the way. Measured cruise phase dose rates come out to 1.84 plus or minus 0.33 millisieverts per day, roughly 2.9 times worse per day than standing on the Martian surface itself. A detailed 2013 study published in the journal Science calculated the total radiation dose for a full round-trip mission. 180 days of cruise out, 500 days on the surface, 180 days of cruise back. At approximately 1.01 sieverts, 1 full sievert for a single mission. NASA's own career radiation exposure limit for any astronaut, adopted after review by the National Academies in 2021, sits at less than 600 millisieverts, 0.6 sieverts, applied universally, regardless of age or biological sex. Do that division too. 1.01 divided by 0.6 comes out to roughly 1.68. A single conjunction-class Mars mission, of the kind every serious architecture actually proposes, delivers a radiation dose that exceeds NASA's own career safety limit by approximately 68% in one single trip. Before you even factor in whatever radiation exposure that same astronaut might have already accumulated on earlier missions in their career. This is shocking discovery number 2, and it sits at the very center of every serious human Mars mission plan. The standard we currently hold ourselves to for astronaut safety cannot be met by the mission we're actually planning to fly. Something has to give. Either the shielding improves dramatically beyond anything currently demonstrated, or the mission profile changes, or the safety standard itself gets revisited. As of right now, nobody has fully resolved which of those 3 it will be. There are 2 genuinely distinct kinds of radiation hiding inside that overall number, and they behave completely differently. Galactic cosmic rays are a continuous, low-level background of extremely high energy, heavy atomic nuclei, iron and similar particles, arriving constantly from deep space. They are, in a very real sense, almost impossible to shield against completely. The particles carry so much energy that even a modest amount of shielding material can shatter them into a spray of secondary particles, sometimes making the effective dose worse rather than better. Solar particle events are different. Sudden, intense bursts of protons from the sun, lasting hours to days, unpredictable in timing but genuinely shieldable. A small, heavily protected storm shelter inside a spacecraft or habitat is an effective countermeasure, and a large, unshielded solar event could otherwise deliver an acute, potentially lethal dose in a single episode. There's also a genuinely honest, unresolved question sitting underneath all of this. What does this radiation actually do to the body beyond raising cancer risk? Rodent studies exposed to simulated cosmic radiation show measurable cognitive deficits and changes to the central nervous system. But translating rodent brain radiobiology directly onto a human being enduring a 30-month mission isn't something scientists currently consider defensible. A widely circulated claim linking Apollo lunar astronauts to elevated cardiovascular disease later in life rests on a sample of fewer than 25 individuals, and it has been seriously challenged on statistical grounds. Even the standard cancer risk models carry uncertainty factors of 2 to 4 times in either direction. We don't fully know. But the not knowing here is not a small gap in an otherwise settled picture. It sits at the very foundation of whether the whole mission architecture, as currently designed, is one we're comfortable actually flying. There's one more environmental hazard worth walking through carefully, because it's another place where popular imagination and physical reality have drifted apart, and where the actual danger turns out to be quieter and stranger than the dramatic version everyone already has in their head. You may remember the opening scene of a well-known Mars survival film. A violent dust storm, howling winds, hurling debris through the air, nearly toppling an entire rocket, forcing an emergency evacuation. It's a gripping scene. It is also, according to the actual physics, essentially impossible. Peak measured wind speeds on Mars top out around 25 to 30 meters per second, roughly 100 kilometers per hour, genuinely fast by any ordinary measure. But the force any wind exerts depends not just on its speed, but on the density of the air carrying it. And Martian surface air density is only about 0.020 kilograms per cubic meter, compared with Earth's 1.225 kilograms per cubic meter. Run the numbers. A 30 meter per second Martian wind exerts a dynamic pressure of roughly 9 pascals. The equivalent wind speed on Earth that would produce that same 9 pascals of force comes out to about 3.8 meters per second, roughly 14 kilometers per hour, a gentle breeze. The kind that might just barely stir a curtain. A hurricane-force Martian dust storm, in other words, would push against your body about as hard as a light breeze on Earth. It would absolutely move dust around, and it would look genuinely apocalyptic. But it would not knock you down, and it would not threaten to topple a spacecraft. So if the wind itself isn't the danger, what actually is? The real hazard is deposition and darkness, and we have direct, hard evidence of exactly how lethal that combination can be. Global dust storms engulf the entire planet roughly every 3 to 4 Mars years, about 6 to 8 Earth years, with major events recorded in 1971, 2001, 2007, and 2018. During the 2018 storm, the Opportunity rover measured an atmospheric optical depth greater than 10 at its location, the highest dust opacity ever recorded from the Martian surface. At that level, transmitted sunlight drops to well under 1/100% of its normal value. The sun doesn't just dim. It stops being a distinguishable object in the sky at all, reduced to a faint smear somewhere behind a deep, dust-brown twilight that can persist, unbroken, for weeks. Opportunity ran on solar power. It went silent during that storm and never woke up again. Curiosity, sitting elsewhere on the planet at the same time, ran on a small nuclear power source instead, and it kept working straight through the entire event without interruption. This is shocking discovery number 3, the cinematic version of a Martian dust storm. Violent wind tearing apart hardware simply isn't physically possible given how thin the air actually is. But the real version, patient and quiet rather than dramatic, is genuinely lethal anyway. It doesn't need force. It only needs weeks of near-total darkness, settling gently onto every solar panel and every radiator on the planet to end a mission entirely. One rover died from it. Its neighbor, powered differently, didn't even notice. Let's turn now to the resource that everything else depends on, water. And the first thing to correct here is an assumption almost everyone carries, even after everything we've just covered about how hostile the Martian surface actually is. Mars is not dry. Mars is frozen. There is, by sheer volume, a genuinely enormous quantity of water sitting on and inside this planet. The problem isn't scarcity. The problem is that essentially all of it is either solid ice, buried underground, sitting at the wrong latitude to be useful, or chemically contaminated in ways that make it dangerous to simply drink. Mars's North Polar Cap alone contains approximately 1.6 million cubic kilometers of water ice, roughly 2 kilometers thick, spanning about 1,000 kilometers across during the northern summer, a volume slightly more than half of Greenland's entire ice sheet here on Earth. Radar sounding from orbit shows it layered in thousands of thin strata, each one a frozen record of a distinct climate cycle driven by the slow wobble of Mars's own axial tilt over millions of years. An ice core archive of the planet's climate history, sitting there, entirely unread. The South Polar Cap is smaller in surface area but considerably thicker, and its associated layered deposits bring the total southern ice volume to a roughly comparable 1.6 million cubic kilometers. uniquely capped by a permanent veneer of frozen carbon dioxide, roughly 8 meters thick, that never fully evaporates even in the height of southern summer. A residual layer of literal dry ice that simply never leaves. But polar ice, for all its sheer volume, is nearly useless to any future crew. The poles endure brutal, months-long winters and negligible sunlight for enormous stretches of the year. Exactly where you would never want to build a habitat that depends on solar power. What actually matters is ice buried at the mid-latitudes, closer to where a habitat could realistically operate, and finding it precisely has become an entire scientific discipline of its own. The story of confirming it directly is a good one. NASA's Mars Odyssey orbiter produced the first global hydrogen maps back in 2002, revealing that the uppermost meter of Martian soil, at latitudes beyond about 60 degrees, is rich in ice. Then, in 2008, the Phoenix lander settled the question beyond doubt. Its landing thrusters blew away a layer of surface dust, exposing bright material underneath. Its robotic arm dug a small trench into that material. And over the following several days, the exposed bright patches visibly sublimed away into the thin air. The unmistakable, directly observed signature of water ice sitting just centimeters beneath the surface. More recently, a mapping effort called SWIM has combined radar, thermal, neutron, and surface-shaped data into detailed ice consistency maps at a resolution of about 3 kilometers per pixel, built specifically to answer the one question that matters most for a future crew. Where, exactly, could a mission land and reach usable ice with a shovel rather than needing an entire drilling rig? This is precisely why choosing a landing site for any future crewed mission is, at its core, a water problem before it's anything else. Water means drinking water. It means radiation shielding once it's built into walls. It means oxygen once it's split apart by electrolysis. And combined with atmospheric carbon dioxide, it means rocket propellant for the trip home. It is the single highest leverage resource on the entire planet. And every serious mission architecture bends itself around wherever that ice sits shallowest. Beyond the ice, Mars carries direct, overwhelming physical evidence that liquid water once flowed freely across its surface at scale for a genuinely long time. Jezero Crater, where the Perseverance rover currently operates, preserves an entire ancient river delta, layered sediment sequences that, on Earth, only ever form where a flowing river empties into a standing body of water, complete with a visible delta front and channels carved by floods. Gale Crater, where Curiosity has spent over a decade, recorded an ancient lakebed. Fine mudstones containing clay minerals that require sustained, roughly neutral pH standing water, persisting for periods estimated at anywhere from tens of thousands to millions of years. And across the ancient southern highlands, entire networks of dry valleys branch and fork exactly the way river systems do here on Earth, dated to roughly 3.7 to 4.1 billion years ago. And in 2024, Curiosity added a genuinely strange new mystery to that ancient story. Driving through a channel called Gediz Vallis, one of its wheels cracked open a rock lying in its path. And inside was something that had never been found on Mars before: crystals of pure, elemental sulfur. Native sulfur normally only forms under a narrow, specific set of geological conditions, and no confirmed mechanism currently explains how it ended up there. As of right now, it remains a genuinely open question. Here is where we need to slow down and handle two specific, genuinely exciting claims with real care, because both were reported at one point as major discoveries, and both are now seriously disputed by other scientists. In 2018, a team led by Roberto Orosei reported something extraordinary. Radar reflections from the MARSIS instrument bouncing off material deep beneath the southern polar ice cap that appeared unusually bright, a signature the team interpreted as a body of liquid water roughly 20 kilometers across, sitting about 1.5 kilometers below the surface. Further similar bright patches were reported in follow-up work in 2021. It would have been the first confirmed body of standing liquid water anywhere on modern Mars. But the interpretation has since been seriously challenged. Other researchers demonstrated that frozen clay minerals, extremely salty ice, or simply the way radar waves interfere constructively when bouncing between multiple thin, closely stacked ice layers can all produce an identical bright radar signature, with no liquid water required at all. The original team ruled out one particular alternative explanation involving frozen carbon dioxide in a 2022 follow-up, but the clay and layered ice explanations remain entirely viable. As of right now, there is no scientific consensus. This should not be presented as a confirmed underground lake. It remains a genuinely contested claim. A second, newer claim arrived in August 2024, when a team analyzing seismic data from NASA's InSight lander argued that the Martian mid-crust, somewhere between 11.5 and 20 kilometers down, is best explained by fractured volcanic rock thoroughly saturated with liquid water, potentially enough, if it's really there, to fill a global ocean 1 to 2 kilometers deep. It made headlines around the world as oceans of water found on Mars. But a direct rebuttal published the following year argued that the same seismic data doesn't actually require a water-saturated layer at all, that the measured properties are just as consistent with other, entirely dry crustal compositions. And even if that deep water turns out to be genuinely real, it's worth remembering exactly how inaccessible it would be. 11.5 kilometers is roughly the depth of the Mariana Trench, deeper than any well ever drilled on Earth with full logistical support. It would be scientifically fascinating. It would also be, for any foreseeable early Mars crew, completely irrelevant. We don't know, in either case, whether there's actually liquid water down there. But the honest uncertainty itself tells you something important. Even after decades of orbiters and landers and rovers, the single most basic question about Mars, where exactly is the water we could actually use, remains genuinely unresolved in its most dramatic possible form. What we do know for certain is shallower, less romantic, and considerably more useful. The ice within a meter or two of the surface, mapped, confirmed, and waiting. Now we arrive at the discovery this entire story has been building toward. The single largest, most consequential gap in the entire body of Mars survival science. Humanity has extensive, exhaustive medical data on the human body at Earth's full gravity. That's every hospital on the planet, every textbook of physiology ever written, thousands of years of direct observation. We also have extensive data on the human body at microgravity, essentially zero gravity, accumulated over more than 25 years of continuous human occupation of the International Space Station. What we have almost nothing on is anything in between. A handful of Apollo astronauts spent up to 3 days at a time at the Moon's gravity, about 17% of Earth's. Nowhere near enough time to reveal any meaningful long-term physiological pattern at all. Mars sits at 37.8% of Earth's gravity. Not 0. Not 1. Something specific in between. And in the entire recorded history of human spaceflight, no human being, no laboratory mouse, no plant has ever been tested at that specific gravity level for any duration long enough to actually matter. This leaves one of the most consequential open questions in the entire field completely unanswered. Does the human body's adaptive response to reduced gravity scale in a straight line? In which case Mars gravity would produce roughly 62% of the harm that full weightlessness does. Or is there instead some minimum threshold of loading above which bones and muscles are able to maintain themselves adequately on their own? Nobody knows which of these is true. Both are entirely consistent with everything we currently understand, and they would imply radically different mission designs, radically different countermeasures, and radically different levels of risk for the very first crew that ever actually steps onto the Martian surface. Every single physiological effect we're about to walk through. Bone loss, muscle atrophy, cardiovascular deconditioning, has only ever actually been measured at zero gravity, aboard the space station or here on Earth at full gravity. Mars itself remains, quite literally, untested ground for the human body. Using the only real data we have, from decades of astronauts living in genuine weightlessness, gives us at least the outer boundary of what's physically at stake. even without knowing exactly how much of it applies at Mars's specific gravity. Bone. In true microgravity, weight-bearing bone loses mineral density at roughly 1 to 1.5% per month, concentrated in the hip, the femoral neck, and the lower spine. For comparison, untreated postmenopausal osteoporosis here on Earth typically progresses at about 1 to 1.5% per year. An astronaut in orbit, in other words, loses bone density at roughly 12 times the rate of an untreated osteoporosis patient, meaning a single 6-month stint aboard the space station can produce bone loss comparable to 2 full decades of ordinary human aging. And the recovery, once back on Earth, is not guaranteed to be complete. A detailed study using high-resolution imaging on 17 returning astronauts found that 9 of them, more than half, had not fully recovered their tibia bone density a full 12 months after landing, with the internal microscopic scaffolding that actually determines fracture resistance still measurably degraded. A 4-year follow-up confirmed that incomplete recovery can persist well beyond a single year. Some of this loss, for some astronauts, may simply be permanent. A crew arriving at Mars after 200+ days in transit would step out onto the surface with skeletons measurably weaker than the ones they left Earth with. And Mars, unlike a returning space station crew, offers no ambulance waiting on the tarmac. Muscle, heart, and eyes. Without deliberate, disciplined countermeasures, leg and back muscle mass can decline by as much as 20% within just 5 to 11 days in orbit, and up to 30% on longer missions, with the body actively converting endurance-type muscle fiber into a type better suited for short bursts of effort it will rarely actually need in space. Meanwhile, without gravity constantly pulling blood down toward the feet, roughly 2 liters of fluid shift upward toward the head and chest within the first few days of any mission. The heart, no longer working against that familiar downward pull, physically shrinks. Cardiac mass and blood plasma volume both decline by roughly 10 to 15%, producing the well-known effect of returning astronauts who are unable to stand unassisted. On Mars, there is nobody standing by with a stretcher to catch them, and perhaps most concerning of all is something called spaceflight-associated neuroocular syndrome, a cluster of changes including swelling of the optic disc, flattening of the eyeball itself, and folding of tissue inside the eye, believed to be driven by a modest, chronic rise in pressure inside the skull from all that headward fluid shift. Roughly 15 to 20% of long-duration astronauts develop clinically concerning versions of this. Broader vision changes, some requiring different glasses in space than on the ground, show up in somewhere between 60 and 69% of astronauts after long-duration missions. No reliable countermeasure currently exists, and a pilot whose vision has quietly, measurably changed is a genuinely serious problem during the single highest stakes maneuver of the entire mission, the landing itself. Immune system, kidneys, and the medicine cabinet. Spaceflight measurably disrupts immune function and reawakens dormant viruses already living quietly in most adult bodies. Herpes viruses like Epstein-Barr and chickenpox's varicella zoster, which can reactivate and begin shedding, without necessarily causing obvious symptoms, inside a small, sealed, recycled air environment shared by only 3 or 4 other people for months at a time. Separately, one of the most comprehensive integrated studies to date, drawing on both human and animal data, concluded that spaceflight measurably remodels the structure of the kidney's internal tubules, with radiation-related damage that appeared permanent in animal models. And the study's own authors concluded that dialysis requiring kidney damage is a plausible outcome of a full Mars round trip. And even the medicine cabinet itself becomes a liability over a long enough mission. An analysis of the entire International Space Station medical formulary, 91 different medications, found that 54 of them have a terrestrial shelf life of 36 months or less, meaning roughly 60% would be expected to expire before a typical 3-year Mars mission even concludes, with no resupply possible anywhere along the way. The single richest dataset in the history of human spaceflight biology comes from an experiment that nature itself made possible. Astronaut Scott Kelly spent 340 days aboard the space station while his identical twin brother, Mark, also a former astronaut, remained on Earth as a genetically matched control subject. 10 separate research teams spent years analyzing the results. Some of what they found was genuinely strange and remains only partly explained even now. Scott's telomeres. The protective caps on the ends of his chromosomes, which typically shorten with age and stress, actually lengthened during his time in orbit, the opposite of what researchers expected, before shortening rapidly again once he returned to Earth. Some ended up shorter than they'd been before he ever left. Nobody has fully explained why. Gene expression changed extensively during his mission, and roughly 91.3% of those changes returned quietly to their normal baseline within 6 months of landing. But about 7% did not. They persisted, specifically in genes tied to immune function, to DNA repair, and to bone formation. The exact same systems we've just spent the last several minutes walking through. The honest caveat, the one any careful telling of this story has to include: this is a single data point. One person, one flight, one genetically matched brother back on Earth. It's the richest, most detailed human spaceflight dataset that exists anywhere, and it is also, unavoidably, a sample size of one. Here's where the story shifts from the purely physical to something quieter, and in its own way, just as serious. And the most important thing to understand about Mars isolation is that it isn't really about loneliness at all, in the ordinary sense. It's built directly into the geometry of the solar system. We actually have rich human data on this, because you don't need a rocket to run most of this experiment. You can run it right here on Earth, inside a sealed chamber or a research station, and people have. In 2010 and 2011, 6 men spent 520 consecutive days sealed inside a 550 cubic meter facility outside Moscow called Mars 500, deliberately including a simulated communication delay to Earth. Objective wrist-worn activity monitoring produced the most robust finding: a steady, progressive decline in overall physical activity across the entire mission, with sleep and rest time slowly expanding at the direct expense of active waking hours. One crew member's entire sleep-wake cycle drifted completely free of the imposed 24-hour schedule, settling instead into a roughly 25-hour rhythm and running desynchronized from the rest of his own crew for extended stretches, inside a facility that was deliberately keeping strict 24-hour time. Sleep duration increased across the mission, while sleep quality itself declined. Crew members reported feeling less stressed and less emotionally disturbed as the mission wore on, which the researchers interpreted, at least in part, as a kind of psychological withdrawal, since communication with the outside mission control team also declined noticeably over the same period. Then, in the final 20 days, as the end of the mission finally became something the crew could actually picture, activity levels spiked sharply back upward. A separate American analog, called HICEUS, ran 6 missions inside a dome on Hawaii's Mauna Loa lava fields between 2013 and 2018. Its 4th mission successfully ran the full year, 365 days. Its 6th mission, beginning in February 2018, was suspended after just 4 days, following an ordinary accident and a crew injury, and was subsequently cancelled entirely after a crew member chose to withdraw. This detail is worth narrating on its own because it's genuinely more revealing than it first sounds. A mission specifically designed to test whether people could endure 8 months of deep isolation ended, instead, in 4 days. Not because of the isolation at all, but because of a completely mundane accident. Real missions, it turns out, tend to fail for real, unglamorous reasons. The single longest-running, most physiologically instrumented human isolation dataset on Earth actually comes from Antarctic overwintering stations, and it has produced its own distinct vocabulary. Winter over syndrome describes a documented pattern of insomnia, cognitive impairment sometimes nicknamed the Antarctic stare, irritability, mild depression, and absent-mindedness. Station doctors have described crew members forgetting, mid-sentence, what they were even in the middle of saying. The third quarter phenomenon is a remarkably reliable mood decline that shows up at roughly the 3/4 mark of any long confinement, seemingly regardless of the mission's total length. Triggered, it seems, by the specific realization that the psychological relief of halfway there has already passed, while actual release still feels remote. Polar T3 syndrome describes a measurable shift in thyroid hormone metabolism during a long overwintering stint, producing genuinely hypothyroid-like cognitive and mood symptoms. A real physiological effect, not merely a psychological one. And a long-term analysis of overwinterers found something researchers described as psychological hibernation. A flattened, narrowed emotional range that seems to emerge specifically as a coping adaptation to prolonged, unrelieved confinement. NASA's own CHAPEA, one experiment placed 4 crew members inside a 700 square foot 3D printed habitat at Johnson Space Center for 378 straight days, from June 2023 to July 2024, including a simulated Mars communication delay of up to 22 minutes each way, simulated spacewalks in an indoor sand pit, deliberately Mars-realistic food rationing, and crops grown inside the habitat itself. Comprehensive peer-reviewed results haven't been fully published as of this telling, so any specific claim about exactly what happened to that crew should still be treated as preliminary. But 2 structural facts separate a real Mars mission from every single one of these Earth-based analogues, no matter how carefully designed, and they're worth stating plainly because they change the entire character of the isolation involved. The first is communication delay. One-way light travel time between Earth and Mars ranges from about 4 minutes at closest approach to roughly 24 minutes at greatest separation, meaning a round trip for any message takes anywhere from 8 to 48 minutes. There is no such thing as a conversation across that gap. There is only correspondence. You cannot ask a question and wait for the answer. You send a message and then you simply wait. The second is solar conjunction. Roughly every 26 months, Mars passes almost directly behind the Sun as seen from Earth, and solar interference degrades or completely severs radio communication for approximately 2 weeks at a stretch. NASA routinely commands its own Mars rovers into a deliberate stand-down during these periods, because no reliable command signal can get through at all. A human crew on the Martian surface would be, for roughly 2 full weeks, entirely and genuinely alone. Not through any failure, not by anyone's fault, but simply because a star happens to be sitting directly in the way. And underlying both of those is the deepest structural fact of all. There is no evacuation. On the space station, a return capsule sits docked and ready at all times, and coming home takes hours. In Antarctica, a medical evacuation is difficult and genuinely dangerous, but it remains at least theoretically possible, given enough time and the right conditions. From the surface of Mars, any return trip home requires waiting for the next available orbital window, which could mean waiting well over a year. Every medical emergency, every surgical crisis, every dental problem, every psychiatric episode has to be resolved entirely with whatever people, drugs, and equipment are already physically present on the planet. There is no cavalry coming, and every single person on that mission will know it, every single day, for the entire duration. Let's talk now about the 2 things every single human being needs without exception: air to breathe and food to eat. And the honest state of the science here can be summarized in one blunt sentence. Mars offers no free lunch and no free energy. Everything must be manufactured, and everything manufactured costs power. In 2021, a device roughly the size of a car battery, tucked inside the Perseverance rover, began an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It drew in thin Martian air, compressed it, heated it to roughly 800 degrees Celsius, and passed it through a solid oxide cell that strips a single oxygen atom away from each carbon dioxide molecule. Across 16 separate runs between April 2021 and August 2023, it produced, in total, 122 grams of oxygen at a peak rate of about 12 grams per hour, roughly double its original design target, at a purity consistently above 98%, breathable grade, working reliably across different seasons, different times of day, and different atmospheric conditions. The honest way to frame that number: 122 grams is trivial. It's roughly 10 hours of breathing for a small dog. Its real significance isn't the quantity at all. It's the proof of principle. Before Moxie, making breathable oxygen directly from another planet's atmosphere was pure theory. After Moxie, it's engineering. That's the exact same gap that separates heavier-than-air flight is theoretically possible from an actual airplane leaving the ground at Kitty Hawk. But the honest scale problem is worth sitting with too. A crewed vehicle designed to lift a crew back off the Martian surface needs somewhere on the order of 25 to 30 tons of liquid oxygen. 25 tons is 25 million grams. Moxie produced 122 grams across 16 runs over 2 full years. The required production plant, in other words, needs to generate something like 200,000 times Moxie's total lifetime output, meaning a system running at roughly 100 times Moxie's rate, continuously, for a year or more, drawing tens of kilowatts of power the entire time. That plant does not currently exist anywhere. Building it is a genuinely known, tractable engineering problem. But known and tractable is doing a great deal of quiet work in that sentence. The same underlying pattern shows up everywhere you look. The only long-duration closed-loop life support system humanity has ever actually operated is the space station itself, and it's instructive precisely because it isn't fully closed at all. Roughly 98% of water gets recovered and recycled, including from urine, sweat, and simple humidity in the air, genuinely higher than any municipal water recycling system here on Earth. Oxygen recovered from exhaled carbon dioxide comes in at around 47%, and food recovery sits at 0%. Every single calorie is shipped up from Earth. Growing actual food on Mars is real, but more limited than headlines have sometimes suggested. NASA's onboard growing facilities aboard the station have successfully produced red romaine lettuce, mustard greens, radishes, chile peppers, and dwarf tomatoes, all genuinely eaten by real astronauts. But every one of these is a leafy green or a garnish. Nobody has grown wheat, rice, potatoes, or soybeans at any meaningful scale in space. Separate experiments here on Earth have grown a wider range of crops, including peas, quinoa, and rye, successfully in simulated Martian soil made to match the real thing's mineral composition and grain size. But those simulants, critically, contain none of the toxic perchlorate salts that saturate actual Martian soil, and they're never exposed to the real planet's punishing ultraviolet radiation or its actual surface chemistry. Growing lettuce in a simulated Martian soil sample inside a comfortable greenhouse and growing lettuce in genuine Martian regolith on Mars are meaningfully different experiments, and perchlorate removal remains an active, unsolved area of research. The honest near-term picture is this: the first crews to reach Mars will eat food shipped from Earth. Any plants they grow alongside them will matter enormously for morale. Tending something green and living has a well-documented psychological benefit. And for delivering fresh vitamins that degrade in long-stored rations, but not for actual calories. Full agricultural self-sufficiency is a problem for a much later era of permanent settlement. It is not a problem the very first expedition will solve. Every successful Mars mission ever flown has used what's called a Hohmann transfer, the lowest energy elliptical path between the two planets' orbits, and every one of them has taken somewhere between about 200 and 270 days one way. Curiosity, 253 days. Perseverance, 203 days. There is no meaningfully faster option available with any propulsion system that currently exists. You can spend more propellant to shave off some time, but you pay for it twice, because arriving faster also means arriving at a higher velocity, which makes the already difficult landing problem measurably worse. And orbital mechanics dictates almost everything that happens after arrival in a way that regularly defeats people's intuition. A conjunction-class mission, the sensible, lower energy option, spends 6 to 8 months traveling out, roughly 500 days waiting on the Martian surface for the next favorable return window, and another 6 to 8 months traveling home, a total of about 2.5 years. An opposition-class mission, the shorter option, spends only 30 to 90 days on the surface, but the return leg swings back closer to the sun, often via a flyby of Venus, actually taking longer overall and costing significantly more propellant, all while increasing exposure to solar radiation. The total mission length still comes out to around 600 days. Here's the detail worth sitting with slowly. There is no version of this where you visit Mars for 2 weeks and simply come home, the way an airline flight works. You can take a shorter total trip with almost no time actually spent on Mars in it, or a longer total trip with 1.5 years of Mars in it. The planets themselves simply will not permit anything in between. We've already covered how the cruise phase delivers worse radiation than the surface itself. Layer on top of that everything from the human body section: the bone loss, the muscle atrophy, the cardiovascular deconditioning, the possible vision changes, and you arrive at the single most uncomfortable sequencing problem in the entire mission plan. A crew spends upward of 200 days steadily losing bone density, muscle mass, and cardiac strength in microgravity. Then, within a single hour, they must execute the highest workload, highest consequence maneuver of the entire mission: a supersonic atmospheric entry at roughly 7.5 kilometers per second, and step out immediately afterward into 0.38 G, in bodies that have spent the better part of a year forgetting what carrying any real weight actually feels like. On the space station, returning crews are carried out of their capsule by support staff waiting on the ground. On Mars, there is nobody there to carry anyone, and the landing itself remains, arguably, the single largest unsolved engineering problem in this entire story. Mars has, in a sense, the worst possible atmosphere in the solar system for landing anything large, thick enough to generate serious, destructive heating on the way down, but nowhere near thick enough for parachutes alone to slow a heavy vehicle to a safe speed. Perseverance's own descent, famously nicknamed 7 minutes of terror, required, in careful sequence, a heat shield, the largest supersonic parachute ever flown at Mars, heat shield separation, radar-guided terrain navigation, a rocket-powered descent stage, and finally a hovering sky crane, lowering the rover itself on cables to the ground. That entire elaborate sequence delivered a 1,025 kilogram rover inside a 440 kilogram total entry vehicle safely to the surface. That is the current record. Nothing heavier has ever landed on Mars. A crewed lander would need to be somewhere in the range of 20 to well over 100 tons, 1 to 2 full orders of magnitude beyond that existing record. Parachutes simply do not scale to that mass in Mars's thin atmosphere. The canopy area required becomes physically unbuildable. The only credible approach currently proposed is something called supersonic retropropulsion, firing engines forward directly into the oncoming supersonic airflow to slow the vehicle down. It's a real, demonstrated technique. SpaceX has successfully used a version of it landing Falcon 9 boosters back on Earth. But it has never once been demonstrated at Mars's specific atmospheric density, at Mars's entry velocities, or anywhere near the mass of a crewed vehicle. The physics of it isn't in serious doubt. The actual engineering simply hasn't been done yet. And until a Starship-class vehicle genuinely lands intact on Mars, for real, every plan built on top of that assumption remains exactly that, an assumption. And once the trans-Mars injection burn is complete, the moment the spacecraft actually commits to leaving Earth's orbit for good, there is no turning back. Orbital mechanics permits only what's called a free return trajectory, a path that loops around Mars without stopping and swings back to Earth. And that path has to be built into the trajectory from the very beginning, forgoing any actual landing at all. Combined with everything we've already covered about isolation and the complete absence of resupply, this produces the single defining condition of any real Mars mission. From the moment that engine burn ends, the crew's survival depends entirely on the hardware and the people already aboard for roughly 2.5 years, with no exceptions. Nothing in the history of human exploration is quite like it. Antarctic overwinterers can, in true extremity, be flown out. Submarine crews can surface. Apollo 13 was 3 days from home when everything went wrong. A Mars crew, in the moment something goes wrong, is not 3 days from anywhere. There's one more thread to this story, and it might be the most quietly devastating one of all. because it isn't about physics or biology at all. It's about what happens after the science actually succeeds. Curiosity's discoveries in Gale Crater converted Mars may once have been habitable into something considerably stronger. Mars was habitable. Ancient lake sediments requiring sustained, gentle, roughly neutral water. Preserved organic molecules, 3 billion years old, still detectable in the mudstone. Proof that if biological signatures had existed there, the geological record was capable of preserving them. And that unexplained native sulfur discovery we mentioned earlier, still sitting there, unresolved. Then, in July 2024, Perseverance drove over an arrowhead-shaped rock in a channel called Neretva Vallis and cracked it open. Inside was organic carbon-bearing mudstone dotted with tiny, sub-millimeter nodules that scientists have nicknamed leopard spots, rimmed with iron phosphate and iron sulfide in patterns that, here on Earth, are very often produced by microbial activity. In September 2025, the mission's science team published a peer-reviewed paper describing this as a potential biosignature. The precise wording matters enormously here and deserves to be stated with real care. This is not a detection of life. A potential biosignature, in the careful technical language scientists actually use, means a feature that could plausibly have a biological origin, for which non-biological explanations have not yet been fully ruled out. The exact same mineral textures can, and sometimes do, form through purely chemical processes with no living organism involved at all. Telling the two apart requires laboratory instruments far more sensitive and sophisticated than anything that can currently be flown to Mars and operated remotely. Which is precisely the argument for bringing an actual physical sample home. And this is where the story turns genuinely poignant. Perseverance is currently carrying 33 sealed sample tubes, gathered specifically for eventual return to Earth, including the very core containing that potential biosignature. But the dedicated Mars sample return program, designed to actually go get them, has run into severe difficulty. An independent review in 2023 found its projected costs had ballooned from roughly $5 billion to somewhere between $8 and $11 billion, with the return date slipping toward 2040. Budget proposals since have called for cancelling the program outright, while NASA has explored cheaper alternative architectures without settling on a final path. As of this telling, the most responsible way to describe the situation is structural rather than definitive. Quite possibly, the single strongest physical hint of ancient life ever found beyond Earth is sitting, right now, sealed in a titanium tube on the floor of Jezero Crater, with no funded, scheduled mission currently in place to go and bring it home. Meanwhile, China's own Tianwen-3 mission is targeting a launch in 2028 and a return to Earth around 2031, which would potentially make China the first nation ever to bring a piece of Mars back to our own planet. We found the thing. And then, for now, we couldn't afford to go get it. It's worth placing this alongside the 60-year pattern of crewed Mars dates that we opened tonight's story with, because it's the same pattern playing out again, in a different key. In 2016, 5 uncrewed cargo landings were promised for a 2026 window. Reality, as of this telling, the vehicle intended for that mission is still inactive, iterative flight testing and orbital propellant transfer, an absolute prerequisite for reaching Mars at all, has not yet been demonstrated even once. NASA's own official architecture points to the late 2030s or 2040 for any crewed mission, with no funded program of record carrying an actual launch date attached to it. China has stated a goal of a crewed landing around 2033, though it has not yet flown a single crewed lunar mission of its own. Independent experts surveyed on the question generally converge on the 2040s as the more realistic window, contingent on several things that haven't happened yet. Demonstrated orbital refueling, a demonstrated large mass landing at Mars, a fully qualified deep space life support system, and a level of radiation risk that regulators are actually willing to formally accept. Every single Mars date anyone has ever confidently announced across 60 straight years has turned out to be optimistic, usually by a factor of roughly 2. That isn't cynicism. It's simply the pattern, stated plainly. The same way Percival Lowell's confident canals eventually gave way to Mariner 4's confident dead rock, which gave way to Mariner 9's confident ancient rivers. Mars has an extraordinary, well-documented history of humbling our confidence. There is no particular reason to think our confidence about exactly when humans will finally walk there is somehow exempt from that same pattern. Given everything we've now covered, the radiation, the cold, the dust, the near vacuum pressure, what would an actual, livable habitat need to look like? Not, it turns out, like the gleaming glass domes of science fiction. The only radiation countermeasure that reliably works is simply mass, placed directly between the crew and the open sky. For Martian regolith, meaningful protection against galactic cosmic rays requires something in the range of 1 to 2 meters of packed material overhead, with some proposals extending to as much as 5 meters for a long-duration habitat. And the physics has a genuinely unpleasant middle zone. A thin layer of shielding can actually make things worse by shattering incoming heavy particles into a shower of secondary particles, including neutrons, that are themselves biologically damaging. You need enough mass to absorb the secondary shower too, which is exactly why a little bit of shielding can be worse than either none at all or a great deal. This is why nearly every serious habitat design converges on the same basic look. Small, thick-walled, mostly buried underground or heaped over with loose regolith, with as few windows as physically possible, because every single window is a hole punched straight through the shielding. The single most futuristic structure human beings will ever build is very likely going to look, from the outside, like a low bunker with a molehill piled on top. There is one genuinely elegant shortcut hiding in the Martian landscape itself, though. Shielding you wouldn't have to build at all. Because Mars's gravity is so much weaker than Earth's, its volcanic lava tubes can grow far larger than any equivalent on Earth before their roofs collapse under their own weight, potentially reaching widths of up to 250 meters, compared with roughly 15 to 30 meters for the largest known lava tubes on Earth. Orbital images have already spotted collapsed skylights, leading down into several of these. One near Pavonis Mons is estimated at 160 to 190 meters across and at least 115 meters deep. A tube that size, buried under hundreds of meters of solid volcanic rock, would offer near-total radiation shielding, remarkably stable temperatures, and complete protection from dust and micrometeorite impacts. Essentially for free, requiring only that the openings be sealed and pressurized. It may be the single most valuable piece of real estate on the entire planet. No mission has ever attempted to actually enter one, and underlying every single one of these systems, oxygen production, water mining, propellant synthesis, crop lighting, thermal control, everything, is a single number that quietly decides whether any of it is actually possible at all: power. Mars receives only about 43% of the sunlight Earth does, and that number drops further under dust, at higher latitudes, and across the roughly 12-hour Martian night. And it can collapse to nearly nothing for weeks during a global dust storm, exactly the mechanism that killed Opportunity. This is the real, unglamorous reason nuclear power keeps reappearing in every serious Mars architecture. NASA's small experimental kilopower reactor completed a 28-hour full-power test run in March 2018, demonstrating a design that can scale up to somewhere between 1 and 10 kilowatts of continuous electrical output. Genuinely useful, but still a fraction of what an actual base, and especially its oxygen and propellant plants, would ultimately require. A nuclear reactor on Mars isn't a preference or a political statement one way or another. It's close to a physical requirement because you simply cannot run an industrial chemical plant on solar panels that a dust storm is capable of switching off entirely for a month at a time. And it's worth closing this section with one honest correction to a very old dream. For decades, people have imagined eventually terraforming Mars, thickening its atmosphere back up, warming it, making it Earth-like again. The actual numbers make this considerably harder than popular imagination usually allows. The total carbon dioxide that could realistically be mobilized from Mars's polar ice and its regolith comes out to roughly 20 millibars of pressure. Warming the planet enough to bring its temperature close to the melting point of ice would require something on the order of a full bar of pressure, roughly Earth's own sea-level atmosphere. 20 millibars against 1,000. The accessible carbon dioxide provides something like 2% of what would actually be needed. And interestingly, the old worry that any thickened atmosphere would simply be stripped away again by the solar wind turns out not to be the real obstacle at all. At the currently measured escape rate, a full 1 bar atmosphere would take on the order of 3 billion years to leak away. The problem was never really about keeping a new atmosphere. It's that there was never enough available carbon dioxide sitting on the planet to build one in the first place, at least using any known method available to us right now. Making Mars into something resembling Earth remains, honestly, a project firmly in the territory of speculative engineering, not a foreseeable near-term achievement. Sit with everything we've covered tonight, all together, for a moment. An atmosphere so thin your own saliva would boil in seconds without protection. Radiation that already exceeds a career safety limit in a single trip. Cold that inverts itself between your boots and your head twice a day. Dust storms that can't knock you down but can kill your only power source through darkness alone. A gravity level that has simply never been tested on a living human body for any meaningful stretch of time in the entire history of our species leaving the ground. An isolation with no possible evacuation, structured directly into the geometry of 2 orbiting planets. And a body that would arrive at all of this, having spent the better part of a year quietly losing bone, muscle, and cardiovascular strength, with nowhere on the whole planet offering so much as a stretcher. By any purely rational accounting of risk and reward, this should be an easy decision to simply not make. And yet here we are, 60 years into confidently, repeatedly, optimistically promising ourselves we're about to go anyway. There is something worth genuinely honoring in that, rather than simply mocking the broken promises. Because this same pattern, reaching for something that current knowledge says is barely survivable, confidently declaring a timeline that later proves too optimistic, and going anyway once the engineering finally catches up, is not a new failure of this particular generation. It's the same pattern that put human beings in wooden boats crossing oceans they didn't fully understand, in pressurized capsules descending into ocean trenches darker and more crushing than anything above the waves, on the summit of Everest without bottled oxygen, standing on the moon in 1969 using computers with less processing power than a modern pocket calculator. Every one of those journeys was, at the moment it was first proposed, an act of confidence running meaningfully ahead of the actual data. And every one of them eventually happened anyway. Not because the risk stopped being real, but because enough careful, patient work eventually closed enough of the gaps between hope and evidence that the risk became one specific people were willing, with open eyes, to accept. Mars is, right now, tonight, sitting in exactly that gap. The physics of getting there is understood. The chemistry of making oxygen and propellant from its own thin air has been directly demonstrated in miniature by a device the size of a car battery. The biology of what awaits a human body once it arrives remains genuinely, honestly unknown in its most important single respect, an entire level of gravity nobody has ever actually tested. We don't know, with real certainty, whether a human being can be kept alive and reasonably healthy on Mars for the 2.5 years a real mission actually requires. But we know, with far more precision and far more honesty than any generation before us has ever had, exactly where every one of the remaining gaps sits, which is, itself, a kind of progress that all those maps of confident canals and confident dead rocks and confident habitable rivers spanning a century and a half of being wrong about Mars could never quite offer. Picture it, one last time, before we close. Somewhere on the floor of Jezero crater, sitting in reddish dust that has not moved in 3.5 billion years, there is a small sealed titanium tube. Inside it, a core of ancient mudstone, carrying organic carbon and strange sub-millimeter mineral spots that might be the closest thing to direct evidence of life beyond Earth that our species has ever laid hands on. It is not going anywhere. It has already waited 3.5 billion years. It can wait a while longer. And somewhere else on that same dusty, radiation-soaked, whisper-thin-aired planet, an idea is quietly waiting too. The idea of an actual human being standing there, breathing air made from the very carbon dioxide surrounding them, drinking water pulled from ice buried a meter beneath their boots, sheltered under a roof of packed red dirt thick enough to hold back the sky's own radiation, looking up at a sun 3/5 the size it appears from Earth. We don't know exactly when that will happen. Every date we've ever confidently given ourselves, across 60 straight years, has arrived late, or not arrived at all. We don't know exactly what that person's bones or heart or eyes will actually do, sustained for months at 38% of the gravity they evolved inside of, because no living creature has ever stayed there long enough to tell us. We don't know if the sealed tube of ancient mudstone will ever make it home to a laboratory capable of finally answering the question it's quietly holding inside itself. But we know, with a clarity no earlier era of this dream ever had, exactly what stands in the way. We have measured the radiation in exact millisieverts. We have watched real oxygen, real breathable oxygen, made from real Martian air by a machine the size of a toaster. We have found real ice, a shovel's depth down in specific mapped locations. We have identified the one gap, a single level of gravity never tested, that everything else quietly depends on. That is not a small thing to know. It is, in its own quiet way, the exact same kind of stubborn, patient attention to a small, inconvenient number that once let a man named Kepler trust an 8 arc-minute error smaller than a strand of hair over 20 centuries of confident philosophical assumption, and in doing so, hand every future mission to Mars its own working laws of motion 400 years before departure. We are the species that keeps doing this, distrusting our own comfortable assumptions, measuring the gap precisely rather than looking away from it, and going anyway once enough of the gap has finally, patiently been closed. Tonight we asked whether we can actually survive Mars, and the honest answer, gathered from everything we've walked through, is neither a simple yes nor a simple no. We found that the atmosphere is a near vacuum that would boil your body's own water within seconds, though not in the violent, explosive way fiction has always promised. We found a radiation environment that already exceeds a career safety limit in a single round trip, with real, open questions about what it does to the body beyond raising cancer risk. We found cold that inverts itself between your head and your feet, twice a day, and dust storms whose real danger is darkness rather than force. We found water in genuinely enormous quantities, just almost entirely frozen, buried, or chemically hostile, and 2 tantalizing claims of deep liquid water that remain honestly, unresolvedly contested. We found the single largest gap in this entire field, a level of gravity sitting precisely between everything we've tested at 0 and everything we've tested at 1, that no human body has ever experienced for any meaningful stretch of time. We found an isolation that isn't emotional so much as structural, built directly into the light speed delay between 2 planets and into the simple absence of any possible rescue. We found that making air and food from nothing requires closing gaps measured in the hundreds of thousands of times over. And we found that landing anything heavier than a small car has never once been attempted, let alone accomplished. And we found, threaded through all of it, the same pattern that has followed Mars since the very first person noticed it wandering strangely against the fixed stars, confident conclusions held with total sincerity that the planet has repeatedly, patiently humbled. A civilization that turned out to be an optical illusion. A dead rock that turned out to have ancient rivers. A crude mission that has been promised, with total confidence, in the early 2020s, by 2024 in the 2026 window, and has, every single time, arrived late. So, can we actually survive Mars? Probably, eventually. With enough shielding, enough tested engineering, enough closed loops of water and air, and enough patient attention paid to exactly the gaps we've spent tonight walking through. The physics does not forbid it. Nothing we've covered tonight is a wall. Every piece of it is a gap, measured, specific, and in most cases, actively being closed, one Moxier run and one radar survey and one bone density study at a time. But probably not on the timeline anyone has confidently promised you. Not yet. Not until someone finally tests what a human body actually does at 38% of the gravity it evolved to expect. Not until a titanium tube sitting in Jezero Crater's ancient dust either comes home to a laboratory or doesn't. Not until the pattern that has defined this planet's entire relationship with human confidence, certainty, followed by correction, followed by a deeper, stranger truth, plays out one more time the way it always has. We are, right now, tonight, exactly at the point in that pattern where the confident predictions have been made and the correction hasn't arrived yet. Sleep well, knowing that somewhere above you, a small red world is quietly holding both an ancient mystery and a very old promise. Neither of them resolved, both of them patiently waiting. Good night, and rest well under the stars, and under the one, particular, still unanswered question of the red one among them.